Hello guys, nice to see you. How are you doing?
Hello.
Hi. Good. Good afternoon. I'm fine, thank you. So last time we derived equations for the molar specific heat capacitance under constant pressure and volume, and also considered adiabatic process. In particular, how we can use these two parameters, Cp and Cv, in the like finding the relationship between pressure and volume during an adiabatic process. So we derived equation that P times V in the power of gamma, which is ratio Cp to Cv, is equal to constant. So that is in addition to previously considered relationship between state parameters like isothermal, isobaric, and isophoric processes. Now we also have similar equation for adiabatic process, and that could be used for different applications. So today we will discuss equipartition of energy in terms of considering in more details these degrees of freedom for the atomic molecule, and also distribution of molecules by speed, and also distribution of molecule concentration in external potential field. As an example, could be a gravitational field. So there is like first Maxwell distribution, also by speed. Also there is a Boltzmann distribution of concentration of molecules in external potential field. So we can combine these two distributions. It will be so-called Maxwell-Boltzmann distribution, which will provide information on how many molecules within certain speed range from V to V plus delta V in certain volume dV, y, d, z are present. So that's why we will consider both distributions by speed and distribution of concentration in the external potential field. Okay, so that is our plan for today. And let me switch to the slides so we can start. So as I mentioned earlier, when we have like single atomic case, we have 3 degrees of freedom, which corresponds to only to translational motion, because when we deal with some mathematical point, that's only type of motion which can happen. So each degree of freedom, no matter which is, originates from translational or rotational or vibrational, provides 1/2 kT energy. So of course it depends on temperature. So we have it here. K, we can write KB to be more specific that it's Boltzmann constant, because just K can be used for other parameters. However, so we keep this in mind, but it's not always the case, and definitely it's possible that gases are formed by molecules which are not made from a single atom. So we will consider the atomic case. So let's say we have system of coordinates x, y, z, and we have the atomic molecule. So these are atoms. They are attached, like there is some chemical bond between them, and they are located a certain distance from each other. So if we consider translational motion along all this axis, that will provide already to this 3 degrees of freedom, because this as a system of 2 atoms, they can move similar along this axis as a single atom. However, on top of that, there is a possibility for rotation of this diatomic molecule. So if we have again the same system of coordinates, this is our diatomic molecule. So this is X, Y, Z. What can happen? It can rotate actually about any of these axes. So it can rotate about axis X, can rotate about axis Z, and also rotate about axis Y. However, as you remember, we consider that atoms are mathematical points, so we neglect with their size. And because of that reason, the moment of inertia of this diatomic molecule about axis Y will be negligibly small. So if it is negligibly small, we remember that kinetic energy of rotational motion is defined as 1/2 moment of inertia about axis, let's say Iy times omega square, which is angular frequency of this rotation. So that will also be negligibly small, so it will be considered as 0. So that's why we should only consider 2 axes about which this rotation can happen, and that's why it can add 2 degrees of freedom. So if we have now we consider translational and rotational motion, then the internal energy can be represented as 3 times. So it's 3 degrees of freedom associated with the translational motion times n, its total number of these molecules, times 1/2 kBT. Plus we have 2 degrees of freedom associated with the rotational motion. So we have 2 times n times 1/2 kb T. And that is equal to 5/2 N kb T, or it can be represented in terms of moles and universal gas constant, 5/2 nu times RT. So that is internal energy for the of an ideal gas, considering the atomic molecule, where we have both translational and rotational motion. If we recall the derivation of this molar heat capacitance CV, it was defined as 1/nu times first derivative of internal energy over temperature. And that is equal to 1/nu for this particular case, which we consider translational and rotational motion. D, instead of internal energy, we substitute this expression for internal energy in terms of nu and R, 5/2 nu times R times T, and here is dt. So following the previous discussion, we get 5/2 times R. So as you remember, for monoatomic case, we got CV equal 3/2 times R. So now it is higher because, so what is the physics behind it? It tells us the physical meaning of this parameter CV, molar heat capacitance of ideal gas. It's how much energy should be provided to ideal gas, in the quantity of 1 mole, in order to increase its temperature by 1 Kelvin. If it possess the atoms which form the ideal gas possess only 3 degrees of freedom, then we, with a smaller amount of energy, we can increase temperature by 1 Kelvin. If there is a diatomic system, so it also possesses this ability to rotate. So we also need to spend this energy which is provided to the system, to the ideal gas, to realize this rotational motion. And overall, in order to increase temperature by 1 Kelvin, we need to realize both translational and rotational motion. So that will require more energy, and this molar specific heat capacitance will be higher. So as you remember, there is a relationship between CP and CV. So molar specific heat capacitance at constant pressure is larger, and we discussed last time why it's larger. Do you remember, by the way, why specific heat capacitance of ideal gas at constant pressure is larger than at constant volume? That's because we, during isobaric process, besides heating the system also performs some work, since volume is not constant, that in order to keep pressure constant, some work should be done. So in that case, the energy provided to the system kind of divided into two channels. One is increase of internal energy, another performing work. When we have constant volume, nothing happens in terms of work because volume is constant, work is equal to zero. So all energy results in provided energy results in increased temperature. That's why Cp at constant specific molar heat capacitance at constant pressure is larger than specific heat capacitance at constant volume. So we remember this relationship between them. This relationship is valid for all systems, regardless their degrees of freedom, because that is defined by work which is done on the system or work done by the system, and that's why it's independent from the internal energy and thus from the degree of freedom. So we can apply this equation for all degrees of freedom for mono and diatomic and more atomic molecules, and then we can write that it's equal to 5 times R plus, well, we can just plus R, and that will be 7 times R. So these are values for CV and CP for the atomic molecule when we consider rotation of this the atomic molecule on top of translational motion. However, there is one more option. Oh, by the way, if we consider this gamma, which is the ratio Cp to CV, we get already different value from previous. It will be 1.4. So this also should be taken into account. So a diabatic process will also behave a bit differently for the atomic ideal gas in comparison to single atomic. So that is not all options, because besides rotation, such a system of two atoms could be represented not only in terms of like some rigid system where the distance between atoms is constant, but it actually can be represented as two atoms connected with some string. So they have some equilibrium condition, and that equilibrium condition, the distance between these atoms is constant. That defines by the properties of the chemical bond between these two atoms. However, at some point, this system can be disturbed and it starts to oscillate. So vibrate. And that means that we should also take into account two additional degrees of freedom associated with the vibrational motion of such diatomic system. So in that case, total internal energy of the ideal gas will be represented as follows. So we will have 3 degrees of freedom associated with translational motion. Then we have 2 degrees of freedom associated with the rotational motion. and 2 degrees of freedom associated with the vibrational motion. So in total, it will be equal to, can be represented as 7/2 nu RT, and already this CV can be calculated as 7/2 times R. So you see that molar specific heat capacitance already increases, because on top of translational and vibrational, we also consider additional vibrational motion. However, we need to mention one interesting fact about this molar specific molar heat capacitance. Let's consider CV. The fact is that this parameter is temperature dependent. So why it happens and how it looks. So if we plot CV versus temperature in some semi-log scale, we will have this temperature scale. Say here we have 10, here will be something like 100, then 200, then say 500, 1000, 2000. Let's consider it in Kelvin. So, because of quantum nature of the chemical bonds in molecules, like between atoms, the energy of rotational and vibrational motion is quantized. That means that it can possess only certain values and can change only like step-like. It cannot change continuously. It should possess only defined discrete values and change between these values in a step. So taking this into account, in order to initiate vibration, or let's say rotational motion, any rotational or any vibrational motion, we need to provide to the system enough energy, so-called kind of, let's call it some activation energy, which will allow this motion to happen. So if we have very low temperatures, there is no energy for these processes to happen. And that's why at very low temperatures initially, we get values for, even if we have diatomic ideal gas, we get values for CV 3/2 times R, which corresponds only to translational motion. So translational motion is classical motion. It's not quantized, and that's why it is. It doesn't require any activation. So if we have some temperature above 0 degrees, so 0 Kelvin, there is automatically, immediately certain motion, translational motion associated to this temperature, which defines internal energy of the ideal gas. However, at some still relatively low temperatures, but definitely higher than, much higher than 10 Kelvin, something in the range of 100 Kelvin, that thermal energy is already enough to excite certain rotational motion, and it's kind of changing step like to a new value of 5.5 times R. So our molar specific heat capacitance, and it takes then quite large interval of temperatures. So we have only translational and rotational motion. And then when temperatures go beyond 1000 degrees, it changes again and becomes equal to 7 times R, which means that we already have contribution from all three types of motion. So we activate additionally to translational and rotational motion, vibrational motion. So molecules can vibrate with certain frequencies, which require minimum amount of energy for their excitation, and that corresponds to quite high temperature. So that's why even when we deal with the atomic ideal gas, it could be possible that depending on the temperature range when this is considered, it can behave in terms of degrees of freedom as monoatomic when we have only contribution from translational motion, or it can be already as diatomic, but with only rotational or with both rotational and vibrational contributions depending on temperature range. So this should be also taken into account. So with this, we kind of finish our discussion of the molar specific heat capacitance. So we considered pretty much all important aspects of this question. And let us switch to another topic, which is also important, is distribution of molecules or atoms of ideal gas by speed, like first of all. So we already introduced the so-called average speed of molecules, and that is true for all molecules in the system, because we have system of many molecules or atoms, and they move randomly. That's why on average, we always will get some average speed of molecules, which is valid for this particular temperature. However, that is not true when we consider some specific molecules, because we will always have some distribution of speeds which this molecule can possess. That could be quite a wide range, because if you can think about this as follows. So imagine that we have some average speed, but there is a small probability, for instance, that few molecules will be, they interact with each other only within collision. So it is possible that for few molecules from this large amount, they will collide with other molecules in such way that they will hit them from one side. And that means that by hitting them from one side, they will only gain their speed over time, like some relatively long interval of time, instead of changing the direction of its motion randomly, there is a chance that small amount of molecules will keep their direction of motion, and after each collision, it will be in favor of increasing their speed. So there is a chance that small amount of molecules, quite small chance, but there is chance, will possess much higher speed than average value for all molecules. The same, in the contrary, can be for another small fraction of molecules out of this big group of molecules in the container, which are, let's say, not so lucky, and they only start to move, and because of collision, they have to attenuate or like change the direction. So the collisions are managed and happen in that way, which works against increase of the speed of these molecules, so they can be slower than average speed for all molecules. So taking this into account, that obviously will be some distribution of speeds for all molecules, and there is so-called Maxwell distribution, which describes the distribution of molecules by speed. So the number of molecules, let's say some small number delta n, which possess the values of their speed in the interval from v to v plus delta v, so delta v is some small change in speed, can be determined according to this to the following equation. So the ratio delta n to n is total, n is total number of molecules, is equal to 4. Why it doesn't write? Oops. 4 pi. Here is m, mass of the molecule. So we assume that we have pristine gas, so there's all molecules are identical. So we have just mass of the molecule or atom, 2 pi kT, kB, in the power 3/2 times v squared times exponent in the power mv squared divided by 2 kBt and times dV. So that is this kind of a bit complicated equation, which gives us the number dn of molecules within all molecules n, which possess speed in the interval from v to v plus delta v. So this equation is called Maxwell distribution of molecules by speed, and the function, we can also express one function f as a function of speed, 1 over n times dn over dv is equal to 4 pi v squared m divided by 2 pi kb t t in the power of 3 half. And here is the exponent minus mv squared divided by 2kt. So this function is a so-called function of distribution by speed. And what is like some features of this function? If we take integral from 0 to infinity of this function fv times dv, any ideas what it will be equal? So you don't need to integrate this equation, but you can just think about physical meaning of this function. So this function is a function of distribution by speed, provides us the probability of the fact that some molecule will possess a speed equal to v. So if we consider speed interval from 0 to infinity and integrate this function, what should we get? In other words, this question will be can be rephrased. What is the chance that in some container with n molecules at some temperature will be at least that we will find molecules with speed in the interval from 0 to infinity? Since this interval actually takes into account all possible values for speed, because we cannot have negative speed. So the minimum speed is 0 when it doesn't move, and maximum is obviously infinity. So we integrate this function over the whole possible range of speeds. And if we consider whole possible values of speed, that means that it should be equal to unity. So it means with the probability of 100%, you definitely will find molecules within this temperature range. Sorry, within this speed range, because speed cannot be smaller than 0 and cannot be larger than infinity. So that's one feature of this function. Also, if we show graphically this function of distribution by speed will be v velocity, and here like speed, and here will be function f as a function of v. So this distribution function. So that will be something like this. We have small probability of like here of very slow molecules. We have small probability of very fast molecules, as we discussed earlier, based on this just very general physical consideration. And obviously, we will have some so-called most probable speed that the majority of molecules will possess. It will be at the maximum of this function like speed distribution. Also, if we want to know the number of molecules which possess speed in the interval from v to v plus delta v. So now actually that what we need to do, we need to integrate this function. So within this interval, get area in this interval under this function, under this curve, and that will define the probability of having such molecules. If we multiply it by total number of molecules, that will give you the number of molecules which have this possess speed in this given interval. If we, for instance, increase temperature, let's extend this a bit, our like this distribution by speed becomes wider, and its maximum is shifted toward larger speed. So it can be now represented like this. The thing is that now the most probable speed means speed with the majority of molecules possess will be at larger values. So higher temperature, obviously, the majority of molecules should possess higher speed. And what is important, that integral of this distribution, regardless of temperature, means area under this curve from 0 to infinity when we change this speed will be always equal to unity. So the area doesn't change, it will be the same, only shape changes. So also, if, for instance, you want to calculate the some number of molecules, let's say delta n, which will be faster than speed v, some given value, then this delta n should be equal to n. Let's say this is our speed v, and we want to know how many molecules will be in the container with speed higher than speed v. So then we have total number of molecules, and we need to multiply it by this probability that molecule is faster than value v for speed. And for that purpose, we need to integrate this function distribution by speed, fv dv, from this given value v to infinity, because, for instance, this is our goal, to know how many molecules are faster. And faster means from v to infinity. And that will give us the total number of molecules which will be in the container of this ideal gas with speed higher than given value v. So that is pretty much everything for the distribution by speed. Actually, I consider that maybe we can discuss a little bit about molecules in the potential field. So maybe shortly, let us do it for a few minutes. So if gas is in some container, in some volume, where there's no potential field, like there is no gravity, for instance, then concentration of molecules in this container, they should be the same in every point of this volume. However, if there is some potential field which interacts with these molecules, there is some exponential distribution of concentration of molecules. So we can write that concentration of molecules, N, this means number of molecules per unit volume, is equal to N naught times exponent in the power minus EP potential energy over KT. And this N naught is concentration when this potential energy is equal to 0. So, however, if potential energy increases, then concentration of molecules decrease because they want to populate this ground level to be closer to this level with 0 potential energy. In general, this number of molecules, dN, which will be in the volume dV with some given coordinates, will be defined as follows. So number of molecules, dN, is equal to N naught, concentration of molecules at 0 potential energy, times, let us write here exponent like this, because we need to write here a bit more now to make it clear, minus, so these and these are the same, it's just different form to write. So it's more convenient to write because we can put more symbols here. So it will be EP potential energy as a function of position. So we have some given coordinates X, Y, and Z of this small volume dV times K divided by KT. And here will be times dx, dy, dz, which is actually our volume dV. That is so-called Boltzmann distribution, and that gives the distribution of molecules by concentration in external field. So some potential field. So what can be? It can be gravitational field, and that's why we can if we consider gravitational field, we can end up by applying this Boltzmann distribution to so-called barometric equation, which gives the distribution of pressure in isothermal atmosphere. So if we assume that atmosphere possesses the same temperature at all altitudes, then the pressure should change as follows. P naught, it will be pressure at the sea level times exponent minus rho 0, means density of air at sea level, times GH, acceleration of free fall and height at which we want to know the pressure, divided by P naught, pressure at the base level. So you see that according to this equation, which can be obtained based on the Boltzmann distribution, because of this distribution of concentration of molecules in external potential field, pressure with height exponentially decreases. So if we now combine both Maxwell and Boltzmann distribution, and we will ask a question, what will be number of molecules, dn, which will be which will possess speed interval from Vx to Vx plus dVx and so on for all coordinates, Vy and Vz. And not only just about these speeds, but we also will specify also in some small volume dV equal to dx times dy times dz, which is located at some position with given coordinate x, y, z, then we will combine both Boltzmann and Maxwell distributions, and we will get this Maxwell-Boltzmann distribution law. So in that case, dn can be given as n naught times m divided by 2 pi kt kbt in the power 3/2. Then we have exponent. Here we need to take into account both kinetic energy and potential energy. So potential energy from Boltzmann distribution plus kinetic energy from Maxwell distribution divided by kT. And here it will be dVx, dVy, dVz. And on top of that, we need also by multiplied by dx, dy, dz. So it actually gives us number of molecules which are in some small volume dV at position x, y, z. So here EP is function of x, y, z. With speed which fits in the interval from v to v plus dv, but here we just describe it in along all directions. So this is Maxwell-Boltzmann distribution, which gives the most complete information when we need to have distribution by speed, and also need to take into account the presence of some potential field. Okay, that's everything what I wanted to tell you today. Actually, it took a bit too long, but hopefully you still have some time to switch to another class. Okay, thank you very much for attention. Any questions? You can think about this and ask.
No question. Thank you.
Yeah. Okay, thank you for attention. Then see you next time on Wednesday. So we will already go for second law of thermodynamics.
Thank you. Goodbye.
Okay, have a good day. Bye-bye.